Does that clear up the question for you now?
Yeah, pretty much.
The time period lasting. So what is this going to tell you? Find the instantaneous velocity. This gives you a path. You're getting closer and closer to time equals 2. Did anybody actually do it this way? Can someone give me the, so what's the, when you plug in 2.01, does anybody have the actual, this value right there? Does anybody have that? What do you have, Kate? What? 13 point what? Is that exact? 7584. Here's 2 rules about rounding. Don't round into the end. Use the store function on your calculator, and I'll show you that in a second. And then also, when you round at the end, if you're going to, go to at least 3 decimals.
Oh.
Go to at least. I don't care if you chop it off or you round up down, but you have to go to 3 decimals. If you start rounding too early, what happens to your final answers? They can go wildly off. You learn that a whole lot in physics. You can get magnitudes off if you start rounding too early. So you're just doing the slope between these 2 points, right? Does anybody have the slope for this one? What's the slope for this secant line going to be? Anybody have it? 0.16. What's the units on that? Feet per second. Yep. Good.
So what you did was you put the.
We did f of 2.01
Okay, so I did
equals 15.7584. Yes, that's right.
So into the 40t. Okay.
That right there. You got it?
Yep.
On the record here, do you know how to do sine of 0.1 by hand? How do you estimate it? Do you remember from trig, how do you do things like that? How do you estimate it? You know certain exact trig values on the unit circle. You know those exact ones, right? And then there are rules for halving and doubling angle values. So like 0.1 is about, you could double or triple it or quadruple it until you get something that's close to like pi over 2, like pi over 6. Pi over 6 is 1/2, so you have that twice. So you can estimate it by having known values, but is there any way to do that exactly? No, that's why you have a calculator to tell you these values. Going to, specifically Q is x comma sine of 10 pi divided by x. What's the slope from P to Q? 0 minus sine of 10 pi divided by x all over 1 minus x. Exactly. Awesome. Can you flip those? Could you make this sine of 10 pi divided by x over what? Why? Yeah, why? There's no concrete reason to do that other than I tend to not like, I don't like leading negative signs. That's just a preference of mine. I don't like leading negative signs. I like to make the leading term or the numerator positive. Does it matter overall? No. This represents the slope we're trying to find, right? How many x values do we have to plug into that? 11. 2 is the first one. 2, 1.5, 1.4. So in order to expedite this, what are we going to use? Our calculator. Thank you. Y equals, exactly. So we go to Y, turn it on. We go to Y equals. We clear this out. And what was it? It was sine of what?
Sine of 10 pi divided by x.
By x, correct. And then we're dividing it by what?
X minus 1.
Parentheses. We got to make sure we have the proper parentheses. X minus 1, correct. What mode should we be in?
Radian.
Always stay in radian unless you are specifically told otherwise. Always stay in radian. So we equate out of this. Now, if we go back to the main here, we go to vars, y vars, y1. What's the first one we want to evaluate it at? 2. So you can literally do this. Yes, it is.
What's the
Second entry. Hold on a sec. What's the next one we're supposed to do?
1.5.
1.5. So we do 1.5 like this. Close it. Okay. Second entry. And then what's the next value?
1.4.
1.4, right? We press enter. So theoretically, can we just keep on doing this?
Yep.
We could. Is there a way to even make it, how could we make it even easier and get the calculator to tell us just exactly what we want without actually pressing second entry so many times? Make a table, right. So if we actually go to table set, what's our starting value? 2, right? Oh no, we want to go from, what's the smallest value?
It's 0.3.
Oh yeah.
Is it 0.3?
0.5.
The smallest one is 0.5, right? And what's our step going to be? 0.1, right? Correct? So let's do our table here. What do we get? Look at all these values. So there it is from 0.5 to 1.1. Now, do we need all of those values? We're not being asked specifically for all those values, but does it hurt to have more? Not really. So we go back here, and then we just go down, right? 1.2, and what do we end up with? So this thing right here So these are the values we need. We also need a few more, right? We can do a few more, sure. Great. You see it right there. Clip this in. So they ask you to get these values. That's the first step. And I think it asks you one question, right? It asks you specifically what? It says, do these slopes appear to be approaching a limit? What do you notice? Are they approaching a limit? What does it look like? Not. What's the easiest way to show that they're not approaching a limit? Why? What's the easiest way to say they're definitely not approaching a limit? They are scattered, but why specifically? Give me a concrete reason.
There's no pattern.
That's true. There's no apparent pattern. Who knows? There might be, right? But generally speaking, can you describe those values to me? What do you notice about those values? They alternate between what and what?
Positive, negative.
They go positive, negative, negative, positive, negative, negative, positive. You know, they're flipping sign, right? If it's going to approach a value, it better stay either or positive, one or the other. It's jumping around. So does this thing seem like it's approaching a specific limit? No, it does not. It doesn't seem like it. So what do you notice? What's going on? Yeah, it's going pretty berserk, right? Did all those lines show up when we were... Oh, it's going really crazy, right? Where is 1, 0? Let's just trace this. Hold on. We can actually... This is one reason trace is actually nice. If we trace this thing, look at the cursor here. Where's 1, 0?
It's right there. Okay, cool.
It's around. It's hanging. So we're getting close to it. It's buried in there, right? Do you see the cursor bouncing around, kind of?
Yeah.
It's somewhere in there, right? So what should we zoom in on? Let's zoom. I'm serious. What should we zoom in on? Zoom box, right? Let's zoom in around there and see what happens, right? So there's the cursor right there. Let's go a little bit to the left, right? Let's go a little bit to the... Yeah, why has the resolution on these calculators not changed in 25 years? I don't know. Well, no, I got that, but what, seriously, but you could keep the same exact menu and just make the resolution better. That's a minimal bar, and I don't know why. This functionally is exactly the same calculator I used when I was starting in 8th grade. Functionally exactly the same. TI-85. So look, we zoomed in, and look what happened. It went berserk, right? So if we try to draw the secant lines on this, let's just pause. Let's actually, we're zooming in. So theoretically, let's hope it clears up, right? Maybe it'll clear up.
Alright, there we go.
What the heck is going on with this function? It cleared up. So we zoomed in. We are now looking at from like 0.997 to like 1.02. Does that seem to help us at all?
No.
No, it seems to make things even worse. So we zoomed in even further, right?
That looks like a part.
We need to actually go into table set, right? We're trying to go around 1, 0, really close to it, right? So let's start at 0.123, like that. And what's our delta going to be? 0.0001. Sound good? Let's do our table of values. It's negative, right? And does it look like there's a path here? All of a sudden, what's going on? It's positive, negative, right? So let's get even closer and see what happens. So what are we at 0.999? What do we want to start? How about this? 0.1234, right? So it's going to be what? Oh,
You put 2 decimal points.
oh, thank you. Sorry. So table set, one of them. So 0.1234, right? So 0.12341, right? We go to table. Look what's going on here. What's going on? Is it still going berserk?
Yeah.
It's still switching sign. It's still switching sign. Let's do it one more time just to be sure. 0.1234566. So it's going to be 0.1234561. Second table. At a certain point, your calculator freaks out and just starts rounding, you notice, right? So by all you can tell right now, by what you can tell, what's the slope of the tangent line there? Do we have an idea? Okay, we'll leave you there and we'll finish this after you get back from lunch. Come back at 12:05. What should we zoom in around? Yeah, zoom, box. So let's zoom in around a little bit of it, okay? From there, I'm going to go up a little bit above this. I'm going to go a little bit further just so we have a decent window. 1, 0, right? Let's go to here, sure. So here's the function. This is what we should have seen. I couldn't figure out for the life of me why we couldn't get a better view when we zoomed in infinitely. So the point is, this is, and where's 1, 0? We can trace here. 1, 0 looks like it's around, right? Oh, it's right there, right? So there's 1, 0. So we'll clip this in. Remember, y1 is the function. y2 is the what? slope of the secant line, right? It's the slope of the secant line. So these are the values we need to do. Are they still bouncing? Are they still going to bounce all over the place? They are still going to bounce. We're really looking at x and y2 here. So this is the first set of values. But then we want to go up and we want to look at the next ones, right? Here they are. Are they still bouncing from positive to negative? Look at the y2 values. Yeah, they're positive, negative, because when you actually do these, and we can go a bit further if we want to. Let's go a bit further. What does it mean for the slope to be 0? Oh, it's just a, what kind of line is that? All lines are straight. Horizontal. Horizontal. So we have our values here, but are these y2 values, are they oscillating? Are they going from positive to negative? It got worse because we were looking at the equation for the slopes, which go berserk anyway. So what we need to do is we can actually change our table set here. If we want to change our table set, let's start at 0.999 and do the exact same thing we did before, right? Oh, I'm sorry, you need to see it. Thank you. We're starting at 0.999 and our delta value is 0.01. So theoretically, should we see something that's consistent? Theoretically, we look at the table here. Look at the y2 column, everybody. Is that a little better?
Yes.
Yes. It's a little better right there. So it looks like, from both sides approaching the same thing, it looks like? It sure does. It's like both sides. And remember, we're looking at y2 because what is y1 on this?
The sine of 10 pi.
The function, exactly. This right here is the function. This is the slope of the secant line from 1, 0 to x f of x. So it really looks like we're between there. So if we, given this value, given those values, what would our estimate be? Negative 31 point what? 4, 1. Yeah, there's our estimate. And that's a very good estimate. Do you understand what's going on there and what we did wrong before? We were looking at just the wrong graph. There are graphs. Those are really neat graphs. You can keep on zooming in. And what do you keep on seeing? Infinite oscillations. Remember we talked about dense numbers? It's a dense function. It's pretty cool.
Does that mean that like those lines that we were seeing when we...
Of x squared. What's that equal? 4. Done. What value do you get infinitely close to as x goes to 2 of x squared?
Oh, I get it.
The function exists there, so you can actually just plug in 2. This is the big rule here. First big thing. Always check to see if you can plug in the actual value. Can you plug in 2 into the function? So what's the limit actually going to be? 4. 2 squared. That's it. That's totally it. Let's make it a little more entertaining. This one right here, the limit as x goes to 1. What's the difference here? Because you can't plug 1 in. You can't plug it in. So there are certain tacks you're going to take. Here's one of them. Can you simplify? You always ask yourself, can you simplify? Well, this is the same thing as the limit as x goes to 1. Can you simplify the numerator? Ah, you can do that to the denominator. What cancels? So this equals the limit as x goes to 1 of 1 over, what's that equal? Yeah, it does. The only difference between this function and this function, what's the only difference? This function, it's traveling along, and what happens when you get to the value x equals 1? There's a hole there.
Oh, yeah.
What about here? There is no hole. All we've done is we've filled in that hole. That's all we've done.
What is that called?
It's called a removable discontinuity. It's a hole. It's not an asymptote, it's just a hole. So the point is, on the function, on the function, does this function actually exist at x equal 1? No. The function does not exist at x equals 1. But what's the limit? Can you calculate a limit right there? Yes. Okay, first rule of Fight Club was many things.